Have you ever wondered how stalactites and stalagmites, such as the ones found in this cave, form? Caves like this one are composed of limestone, which consists primarily of calcium carbonate. Stalagmites and stalactites arise when the dissolved calcium carbonate in water forms deposits on the cave's floor, ceiling, or walls. The principles of chemistry that explain the formation of these deposits, solubility and precipitation, are the topics of this program. In this program, you will learn the factors that influence the ability of a substance to dissolve in solution. In addition, you will be able to determine the conditions required for the substance to form a precipitate. When you are familiar with the formation of solutions and precipitates, you will see 4 processes used in science and industry to isolate substances from mixtures. A quick review of solution terminology will help you understand the concepts of solubility and precipitation. A solution is a homogeneous mixture of 2 or more substances that are uniformly mixed and in the same physical phase. A solution forms when one or more substances dissolve into another substance. A substance that dissolves when forming a solution is called a solute, and the substance in which the solute dissolves is called the solvent. A swimming pool is an example of a solution. In this solution, water is the solvent, and sodium hypochlorite, a chemical used to kill bacteria in pools, is the solute because it is dissolved in water. Depending on the amount of solute in a solution, the solution can be unsaturated, saturated, or supersaturated. The amount of solute dissolved in solution is analogous to the number of people at a concert. If a stadium, which represents a solvent, can accommodate 10,000 fans, but there are only 7,500 fans in the audience during the opening act, then the stadium is not full. This is similar to an unsaturated solution in which the solvent does not contain as much dissolved solute as it is capable of holding. As time passes, the remaining 2,500 people stroll into the stadium before the headlining band is scheduled to play. At this point, the stadium is full. This is equivalent to a saturated solution because the solvent contains as much solute as it can, just as the stadium contains as many people as it can. Surprisingly, 10 additional people somehow manage to sneak into the concert. The situation when the excess 10 people are in the stadium is analogous to a supersaturated solution because a supersaturated solution contains more solute than the solvent can hold. In addition to not finding a place to sit because there are no seats left, the fans are escorted out of the stadium by security. Excess solute is not escorted out of solution by security. It simply comes out of solution easily. The formation of a solution can be broken into 3 different processes. These processes will be demonstrated with a solid dissolving in water, which forms an aqueous solution. An aqueous solution is one in which water is the solvent. Although the processes are discussed sequentially, keep in mind that they occur simultaneously. In one process, the attractive forces holding the solute particles together must be broken, allowing the separation of the solute. In a similar process, the attractive forces holding the solvent particles together must also be broken. Breaking the attractive forces holding the solvent particles together provides space for the solute within the solvent. In contrast to the first 2 processes, in which attractions are broken, attractions form between solvent and solute particles in the 3rd process. For a solute to dissolve in a particular solvent, the attractions between the solute and solvent must be greater than the attractions keeping the solute together and the attractions keeping the solvent together. The term describing the maximum amount of solute dissolved in a saturated solution at a specific temperature and pressure is solubility. When reporting solubility values, it is important to state the temperature and pressure at which the solution is being made, because temperature and pressure affect solubility. For example, at 25 degrees Celsius and 1 atmosphere of pressure, the solubility of glucose is 110 grams in 100 grams of water. At 70 degrees Celsius and 1 atmosphere of pressure, the solubility of glucose is 350 grams in 100 grams of water. Another factor that influences the solubility of a substance is polarity, which will be discussed next. The polarity of a chemical bond results from the unequal sharing of electrons between two bonded atoms in a molecule. The degree to which an atom in a bond pulls the electrons towards itself is called electronegativity. Bond polarity is determined by comparing electronegativity values of the two atoms forming a bond. Use an electronegativity chart to determine the electronegativity difference between the two atoms. If the electronegativity difference is 0.5 through 1.9, as occurs in the bond between a hydrogen atom and an oxygen atom, then the bond is polar. In a polar bond, the more electronegative atom pulls the shared electrons more closely to itself. Due to the greater density of electrons around the more electronegative atom, in this case oxygen, that atom takes on a partial negative charge, while the less electronegative atom, hydrogen, takes on a partial positive charge. If the difference between electronegativity values is 0.4 or less, as occurs in a bond between a hydrogen atom and a carbon atom, then the bond is nonpolar. In a nonpolar bond, electrons are shared fairly evenly. Therefore, the atoms within the bond do not develop charges. A molecule that possesses more than one polar bond, such as carbon dioxide, is not necessarily a polar molecule. To determine a molecule's polarity, determine the orientation of all the bonds. If the polar bonds within the molecule completely offset each other, the partial charges cancel, and the molecule is nonpolar. In contrast, if the polar bonds do not completely offset each other, as in a water molecule, the partial charges do not cancel, and the molecule is polar. It is important to know the polarities of solvent and solute when making a solution, because the general rule of solubility is like dissolves like. This means that nonpolar substances dissolve within each other, and polar substances dissolve within each other. Two polar liquids, in this case, the methanol and water that make windshield wiper fluid, dissolve within each other, because the attractions between the methanol and water molecules are strong enough to overcome the attractions keeping the methanol molecules and the water molecules together. Nonpolar liquids, such as vitamin E oil and safflower oil, also readily dissolve in each other for the same reason. In contrast, polar and nonpolar liquids do not mix to a significant extent, and in fact, form two distinct layers. The reason nonpolar molecules do not dissolve in polar molecules is because the attractions between a nonpolar solute and a polar solvent are not great enough to overcome the solute-solute attractions and the solvent-solvent attractions. In a sense, the nonpolar molecules are pushed away by the polar molecules. You can see the two different layers formed by water, which is polar, and vegetable oil, which is nonpolar. The like dissolves like rule also applies to solutions of molecular solids dissolved in liquids. Nonpolar solids tend to dissolve in nonpolar liquids, and polar solids tend to dissolve in polar liquids. vitamin tablets provide an excellent example of the like dissolves like rule. The two classes of vitamins are fat-soluble and water-soluble. Vitamins A, D, E, and K are fat-soluble because those vitamins and fat are essentially nonpolar. In fact, fat-soluble vitamins can dissolve in fatty tissue and actually become toxic if the vitamin's concentration is too high. Fortunately, a balanced diet generally does not lead to toxic concentrations. In contrast to the fat-soluble vitamins, the water-soluble vitamins, vitamin B complex and vitamin C, are polar. Therefore, they do not dissolve in fatty tissue. Instead, excess water-soluble vitamins dissolve in water, and they exit the body through the urinary tract. You may be asking yourself, what about solid ionic compounds? Remember, an ionic compound, such as sodium chloride, is composed of a fixed proportion of cations and anions. Do you think ionic compounds dissolve in nonpolar or polar solvents? Ionic solids do not dissolve to a significant degree in nonpolar solvents, but they are generally soluble in polar solvents. The reason ionic compounds dissolve in polar solvents is ionic compounds dissociate, or break apart, into their constituent ions. The ions possess charges, so they are attracted to the oppositely charged ends of polar molecules. Pressure is another factor that affects solubility. Although the solubilities of liquids and solids are not affected strongly by pressure, the solubilities of gases are affected greatly by pressure. The solubility of a gas increases when pressure increases. This pressure chamber will be used to illustrate why the solubility of a gas increases when pressure increases. The gas molecules within the chamber are constantly in motion. Some gas molecules dissolve into solution, while some gas molecules already dissolved in the solution come out of solution. These two processes, the gas molecules dissolving into solution and the gas molecules leaving solution, occur at the same rate and are therefore said to be in equilibrium. In this program, you will see different examples of equilibrium, so it is important to know that equilibrium is a generic term that describes any situation in which a forward process occurs at the same rate as its reverse process. In the chamber, an increase in pressure caused by a reduction in volume results in a greater number of gas molecules per unit volume. The increase in concentration disturbs equilibrium, temporarily causing more gas molecules to strike the liquid's surface and dissolve into solution at a faster rate than gas molecules leave the solution. As a consequence, more gas molecules are forced into solution. Eventually, the rate of gas molecules escaping from solution increases until a new equilibrium is reached. When equilibrium is achieved under the higher pressure, the solution contains more dissolved gas than it did under the lower pressure. The effect of pressure on solubility is analogous to penguins sitting atop an iceberg that suddenly breaks. These penguins represent gas molecules in equilibrium because they hop on and off the iceberg at the same rate, so that there is always the same number of penguins on the iceberg. There are 10 penguins on an iceberg that is initially 10 square meters. Therefore, the concentration is 1 penguin per square meter. If the iceberg's volume is reduced by exactly 1/2, the 10 penguins are suddenly confined to a 5 square meter area, and the concentration increases so that there are 2 penguins per square meter. Since the smaller area is too confining for some penguins jump into the ocean just as some gas molecules enter solution when a higher concentration occurs. At the same time, fewer penguins try to jump back on the iceberg. Eventually, a new equilibrium is established, where the penguins jump off and on the iceberg at equal rates. As you can see at this new equilibrium, there are more penguins in the ocean now than there were when the iceberg was larger. Remember that prior to the iceberg splitting, there were 2 penguins in the water, and now there are 5 penguins in the water. Just as an increase in pressure results in gases becoming more soluble in a liquid, a decrease in pressure results in gases becoming less soluble. An example that illustrates this property nicely is the bottling of carbonated beverages. To make soda, carbon dioxide gas is bottled under great pressure. The increased pressure makes carbon dioxide gas more soluble, so the gas goes into solution. The result is a well-carbonated soda. Removing the lid reduces the pressure within the bottle. Therefore, the contents are no longer subject to the high pressure under which they were bottled. As a consequence, carbon dioxide gas begins to come out of solution to re-establish equilibrium at the lower pressure. The sound you hear and the bubbles you often see when opening a bottle of soda are evidence of the escaping carbon dioxide gas. The solubility of gases in a solution is determined using Henry's law, which states that the solubility of a gas in solution is proportional to the pressure of the gas at a specific and constant temperature. In the equation for Henry's law, S1 divided by P1 is equal to S2 divided by P2. S1 stands for the solubility of the gas at a given pressure, which is denoted as P1. S2 stands for the solubility of the same gas at a different pressure, which is designated P2. Since the solubility of a gas is proportional to pressure, you should note that if pressure increases, the solubility of the gas increases, and if pressure decreases, the solubility of the gas decreases. Remember that the temperature must remain constant to use Henry's law. Consider a situation in which carbon dioxide is bottled at 25 degrees Celsius under 5 atmospheres of pressure, abbreviated as 5 atm. At this pressure, carbon dioxide gas has a solubility of 0.16 moles per kilogram of water. The term for solution concentration expressed in number of moles of solute per kilogram of solvent is molality. Therefore, the units can be simplified to molal. When the bottle is opened, pressure is released, and a new solubility can be determined. Opening the bottle will lower the pressure above the liquid from 5 atmospheres to 1 atmosphere. But suppose you are asked to determine the solubility of carbon dioxide at an intermediate pressure of 3 atmospheres. Moving the pressure, P2, to the left side of the equation allows you to solve for S2. You can now use this equation to solve for the solubility of carbon dioxide at 3 atmospheres of pressure. The solubility of carbon dioxide at 3 atmospheres of pressure is 0.096 molal. When the pressure equals 1 atmosphere, the solubility of carbon dioxide is 0.032 molal. You can clearly see that the solubility of carbon dioxide gas decreases when pressure decreases. Temperature is another factor that affects solubility. The effect of temperature on solubility is not the same for gas, solid, and liquid solutions. In general, the solubility of a gas in a liquid decreases as the temperature increases because the gas particles strike the solution surface more frequently and forcefully, causing the gas particles to escape readily from the solution. The fact that a gas becomes less soluble when the temperature increases has important environmental consequences. Industrial plants often pump cold water from lakes and rivers to cool the heat-generating systems, which increases the water temperature before it returns to its source. In this example, cold water from the lake is used to cool the steam within the turbines, causing them to rotate, and in turn drive the generator. The process of cooling the steam causes the water to gain heat before it returns to the lake. Due to the increased water temperature, the solubility of oxygen decreases, and the returned warm water contains less dissolved oxygen than it did when the water was cold. This means that less dissolved oxygen is available for aquatic animals, which may suffer due to insufficient amounts of oxygen. In contrast to the effect temperature has on the solubility of gases in liquid solutions, the solubility of solids in liquid solutions shows no consistent trend when the temperature increases. Predicting the solubility of a solute in a particular solvent is difficult, and many exceptions occur. A simple way of determining the effect of temperature on the solubility of a solid in a liquid is to perform the desired experiment. For some solutions, such as an aqueous sodium acetate solution, increasing the temperature of the saturated solution when excess solute is present allows the excess solute to dissolve in solution. Slowly cooling the solution to the original temperature allows the excess solute to remain in solution. Therefore, the solution becomes supersaturated, a condition in which the cooled solution holds more solute than expected at a given temperature. It is much like a game of musical chairs. If 5 seats are available when the music stops playing, but all 6 people manage to squeeze onto the 5 chairs, the chairs can be considered supersaturated with players. Supersaturated solutions are very unstable, and a simple tap on the solution's container can cause the solute to come out of solution as easily as a nudge from one of the players can push the extra person out of his seat. The process of a compound, such as sodium chloride or sodium acetate, dissolving in a solvent, such as water, is called dissolution. When ionic compounds dissolve, they break into their constituent ions until the solution becomes saturated with them. Here you see the process of dissolution as sodium fluoride, a tooth decay preventative found in some brands of toothpaste, dissolves in water. At saturation, the solution contains a maximum number of ions, and the number of ions remains constant, although the ions constantly dissolve into solution. At the same rate, ions leave solution and return to the solid state. The process of ions leaving the solution and forming a solid ionic compound is called precipitation, and the solid formed is called a precipitate. Precipitation is shown in a chemical equation by pointing the arrowhead in the direction of the solid. When the rate of dissolution equals the rate of precipitation, the saturated solution has reached equilibrium, which is expressed by a balanced equation that uses 2 arrows pointed in opposite directions. The arrows are pointed in opposite directions to indicate that both the forward and reverse reactions are taking place simultaneously, and that no net difference in product occurs. Here you see the balanced equation for the example of sodium fluoride in equilibrium with its dissolved ions. Remember that in a balanced equation, the number of atoms or ions of each element on the product side of the equation must equal the number of atoms or ions of each element on the reactant side. In this equation, there is 1 sodium ion and 1 fluoride ion on each side of the equation. Remember that a lack of a coefficient or subscript indicates a 1. Knowing how to write balanced equations is important, because the coefficients are used when determining the solubility of ionic compounds. Ionic compounds have different degrees of solubility, meaning that ionic compounds differ in the amount of solute that dissolves in a given amount of solvent. The degree to which ionic compounds dissolve varies from sparingly soluble to highly soluble. Sparingly soluble ionic compounds give off few ions and remain mostly solid, while highly soluble compounds dissolve so much that little or no solid remains. An equilibrium expression is used to determine the solubility of an ionic compound. The equilibrium expression is shown here in its generic form. In an equilibrium expression, the concentrations of the products are placed in the numerator position, and the concentration of the reactants are placed in the denominator position. Each compound or ion in the expression is raised to its coefficient in the balanced equation. Pure solids and liquids are expressed as a constant equal to 1 in the equilibrium expression because their concentrations essentially do not change during a reaction. Since any number divided by 1 remains the same, a 1 representing the concentration of a solid or liquid may be dropped from the equilibrium expression. When discussing the solubility of ionic compounds, the equilibrium expression is referred to as the solubility product constant. The solubility product constant, which is abbreviated as KSP, reflects the solubility of an ionic compound because it is determined from the ion concentrations of a saturated solution at equilibrium. As the name implies, the solubility product constant is a constant at equilibrium, meaning that it has one definite value for each compound at a specific temperature and pressure. As in the equilibrium expression, the coefficient for each ion is used as an exponent of the ion's concentration. Returning to our discussion of sodium fluoride, the solubility product constant is written as the concentration of sodium ions multiplied by the concentration of fluoride ions. Remember that the concentration of a solid is essentially a constant represented by the number 1. Therefore, the concentration of sodium fluoride can be omitted from the equation. At this point, you should notice that the solubility product constant equals the concentrations of ions raised to their appropriate powers, which are determined by their coefficients in the balanced equation. The KSP values for many common ionic solids at 25 degrees Celsius are listed in many chemistry textbooks. Notice that KSP values do not have units. Small KSP values have large negative exponents, indicating that the compound is highly insoluble, whereas large KSP values have small negative numbers, indicating that the compound is very soluble. Using this chart, you can see that copper sulfide has a small KSP value, 8.5 times 10 to negative 45, which indicates it is sparingly soluble in water. Remember that sparingly soluble compounds give off few ions when placed in water. Therefore, they remain mostly solid. In contrast, lead chloride has a larger KSP value in water, 1.6 times 10 to negative 5. This means that more ions dissolve in solution and less of the solid remains. The difference in values also means that lead chloride is more soluble in water than copper sulfide. Consequently, it dissolves to a greater extent. Knowing KSP values allows you to find the ion concentrations at equilibrium. It is important to note that the solution is saturated with ions at equilibrium. Suppose you are asked to determine the ion concentrations for a saturated solution of lead iodide at 25 degrees Celsius. According to the chart, the KSP value of lead iodide is 1.4 times 10 to negative 8. First, write the balanced equation showing how the ions dissociate. Lead iodide is in equilibrium with lead ions and iodide ions. Next, determine the ratio of lead ions to iodide ions by looking at the balanced equation. The coefficient of lead ions is 1, and the coefficient of iodide ions is 2. Therefore, the ion ratio is 1 to 2. Since the coefficient of lead ions is 1, it is expressed as the variable x. And because the amount of iodide ions is 2 times the amount of the lead ions, the concentration of iodide ions is expressed as 2x. Now write the expression for KSP. KSP equals the concentration of lead ions times the concentration of iodide ions squared. The concentration of iodide ions is squared because the coefficient preceding it in the balanced equation is 2. Solve for x by substituting the variables into the KSP expression, which gives the equation 1.4 times 10 to negative 8 equals x times 2x squared. You now want to square 2x, which is 4x squared, before multiplying it by x. Remember that when you multiply two numbers that are raised to exponents, the coefficients are multiplied, but the exponents are added. Doing this gives the equation 1.4 times 10 to negative 8 equals 4x cubed. To solve for x, divide 1.4 times 10 to negative 8 by 4, and then take the cube root. This yields a value of x equal to 1.5 times 10 to negative 3. And multiplying this value by 2 yields 3 times 10 to negative 3. Since x represents the ion concentration of lead, you know that the lead ion concentration at equilibrium is 1.5 times 10 to negative 3 moles per liter of aqueous solution. You also know that 2x represents the concentration of iodide ions, which is 3 times 10 to negative 3 moles per liter of aqueous solution. Since the term molarity expresses concentration in terms of moles per liter of solution, the given units can be simplified to molar. In addition to finding ion concentrations at equilibrium when given a KSP value, you can also determine the KSP of an ionic compound if you know the concentrations of the ions in a saturated solution. For example, when calcium sulfate dissociates, the equilibrium concentration of calcium ions at 25 degrees Celsius is 7.8 times 10 to negative 3 molar. From the balanced equation, you can see that the coefficient of the calcium ions is the same as the coefficient of the sulfate ions. Therefore, the concentrations of calcium and sulfate ions are equal. Since the ion concentrations are equal, the sulfate ion concentration must also be 7.8 times 10 to negative 3 molar. Insert the concentration of 7.8 times 10 to negative 3 molar into the KSP expression for each ion and multiply to solve for KSP. You have now determined that the solubility product constant for calcium sulfate is 6.1 times 10 to negative 5. In all saturated solutions where a solid ionic compound is present, the concentration of ions is in equilibrium with the solid. In this example, solid calcium sulfate is in equilibrium with its constituent calcium and sulfate ions. If you add another solution, such as calcium nitrate, into a test tube containing the calcium sulfate solution. What do you think might happen? Knowledge of Le Chatelier's principle helps answer this question. Le Chatelier's principle states that if a change is applied to a system at equilibrium, the equilibrium shifts to counteract the change and re-establish equilibrium. Changes that can alter equilibrium include changes in temperature, pressure, and the concentrations of reactants or products. The addition of calcium nitrate to a saturated solution of calcium sulfate upsets equilibrium because calcium ions and nitrate ions are added to the solution. The calcium ions are important to note because they appear in both solutions. Adding the calcium nitrate solution to a calcium sulfate solution increases the amount of calcium ions in solution. Using Le Chatelier's principle, you can determine how the additional calcium ions affect equilibrium. According to Le Chatelier's principle, to counteract the excess calcium ions in solution and return to equilibrium, excess calcium ions must be removed. To remove the excess calcium ions, the system shifts to the left, and the calcium ions and sulfate ions combine and produce more calcium sulfate. The additional calcium ions combine with the sulfate ions present in solution until a new equilibrium is established. Ions common to both solutions, in this case the calcium ions, are called common ions. Adding a common ion to a saturated solution lowers the solubility of the ionic compound present. This effect is called the common ion effect. In the previous example, you saw that the addition of calcium nitrate reduced the solubility of calcium sulfate. As a consequence, more calcium sulfate precipitate formed. Unfortunately, since the amount of calcium sulfate precipitate is so small that it would be difficult to see in a video, a saturated sodium chloride solution to which concentrated hydrochloric acid is added is used in this video to demonstrate the common ion effect. In the video demonstration, the common ion is chloride, and the ionic compound that has its solubility lowered is sodium chloride. When solutions containing common ions are mixed, the common ion has a different concentration in the new solution than it did in either of the original solutions. Similar to the way you found the concentrations of ions in a solution at equilibrium, you can find the concentrations of ions at equilibrium in a solution where a common ion is present. Suppose you are asked to find the sulfate ion concentration of a 1 liter saturated solution of calcium sulfate after 0.5 moles of solid calcium nitrate has been added. You are given that the KSP value of calcium sulfate at 25 degrees Celsius is 6.1 times 10 to negative 5, and that the saturated sulfate ion concentration for calcium sulfate in water is 7.8 times 10 to negative 3. The first step in solving this problem is to write the balanced equation for the dissolution of calcium sulfate in water. Calcium sulfate is in equilibrium with calcium ions and sulfate ions. The second step is to use the balanced equation to determine the ion ratio. You should realize there is a 1-to-1 ratio of calcium ions to sulfate ions, since the coefficient of both the calcium ions and the sulfate ions is 1. Now you can assign a variable to the concentration of each ion. Since the ion concentration ratio is 1-to-1, the ions can be expressed as X to X. However, the additional calcium ions from the 0.5 moles of calcium nitrate must be taken into account to determine the sulfate ion concentration in the solution. Comparing the concentration of calcium ions in the original solution, 7.8 times 10 to negative 3 molar to the amount of calcium ions added, 0.5 molar, reveals a difference in calcium ion concentration. Since the amount of ions initially present in the solution is small compared to 0.5 molar, the total concentration of calcium ions is approximated to be 0.5 molar. Therefore, you can use 0.5 molar as the concentration of calcium ions. The next step in solving this problem is to write the solubility product expression. Remember that because calcium sulfate is a solid, it is dropped from the equation. Hence, the expression is written as Ksp equals the concentration of calcium ions times the concentration of sulfate ions. Now substitute the ion concentrations of the mixed solution into the Ksp expression. As determined in the previous scene, the values are 0.5 molar for the calcium ion concentration and X for the unknown concentration of sulfate ions. Solving for X gives 1.2 times 10 to negative 4. This result means that the equilibrium concentration of sulfate ions in the new solution is 1.2 times 10 to negative 4 molar. Do you see that by adding a common ion to this solution, the concentration of sulfate ions has been reduced from 7.8 times 10 to negative 3 molar in the initial solution to 1.2 times 10 to negative 4 in the solution containing the common ion. The reduced sulfate ion concentration reflects the fact that the solubility of an ionic compound is less in the presence of a common ion. In the last few scenes, you learned that adding a common ion to a solution lowers the solubility of an ionic compound. Another factor that may affect the solubility of ionic compounds is pH. pH is a measurement that indicates the relative acidity or alkalinity of a solution. A solution that has a low pH is acidic, and one that has a high pH is basic. In the beginning scene, you learned that stalactites and stalagmites are calcium carbonate formations. Many caverns composed of limestone have been around for millions of years. Nevertheless, the calcium carbonate within the limestone dissolves in water, hollowing the caverns and eventually forming the stalagmites and stalactites. If calcium carbonate is a rather insoluble compound in water as shown by its Ksp value of 8.7 times 10 to negative 9, how does it dissolve from limestone in the first place? In the next few scenes, you will learn how rainwater that seeps into limestone caves becomes acidified and how the lower pH of the water causes calcium carbonate to dissolve. Rainwater is one cause of the dissolution of calcium carbonate in limestone caves. As rainwater falls from the sky and seeps down through the soil, it dissolves carbon dioxide. The dissolved carbon dioxide acidifies the water, forming a carbonic acid solution. Weak acids ionize to a small extent, meaning that they give off only a few ions. Therefore, a small amount of carbonic acid ionizes into hydrogen ions and bicarbonate ions that remain dissolved in water. The acidic water trickles into small cracks where the pressure becomes slightly greater than 1 atmosphere. As you learned earlier, an increase in pressure increases the solubility of gases. As a consequence, more carbon dioxide gas dissolves in water, increasing the concentration of carbonic acid within the cracks. According to Le Chatelier's principle, as the concentration of carbonic acid increases within the cracks, the system must shift right to compensate for the additional carbonic acid. As a result, the concentration of bicarbonate ions and hydrogen ions increases. The hydrogen ions in solution attack the carbonate ion in calcium carbonate, forming more bicarbonate ions, The lower the pH of the solution, the more hydrogen ions are present to strip the carbonate ion from calcium carbonate. You should now see why a lower pH causes an increase in the solubility of calcium carbonate. As the mineral-rich water leaves the small cracks and drips down the cavern ceiling and walls, the pressure is reduced. Under the reduced pressure, the dissolved carbon dioxide becomes less soluble, and some of it escapes from solution as a gas. This causes a shift to the left in the equilibrium of the reactions discussed in the previous scene. As carbon dioxide escapes, less dissolved carbon dioxide is found in solution. Therefore, the carbonic acid breaks down, giving off water and aqueous carbon dioxide. As a consequence, hydrogen ions and bicarbonate ions combine to produce more carbonic acid to maintain equilibrium. Since hydrogen ions are used to form carbonic acid, fewer hydrogen ions are found in solution, so the solution's pH increases, meaning the solution is less acidic. To compensate for the fewer hydrogen ions at this point, the last reaction shifts left, and calcium carbonate precipitates. If these reactions occur while the water drop hangs from the ceiling or walls of the cavern, the calcium carbonate precipitate contributes to formations suspended from the ceiling called stalactites. If the reactions do not occur until the water drop falls onto the cavern floor, then the calcium carbonate precipitate contributes to formations rising from the floor called stalagmites. While it is difficult to mimic the natural conditions under which precipitates form, it is possible to make a desired precipitate by mixing solutions of ionic compounds. Chemists have developed a set of solubility rules for ionic compounds that allow you to determine if the compounds dissociate or remain a solid when placed in water. Say you want to determine if you can make a calcium chloride solution and a sodium carbonate solution that, when mixed, forms a calcium carbonate precipitate, like the compound formed in caves. Checking the solubility rules allows you to verify the compounds that you are using are soluble in water. Rule 4 states that most compounds containing chloride ions, including calcium chloride, are soluble. Therefore, calcium chloride dissociates into calcium ions and chloride ions when placed in water. According to Rule 1, compounds containing alkali metals are also soluble in water. Since sodium is an alkali metal, sodium carbonate dissociates into its constituent ions, sodium and carbonate, when placed in water. Now you need to determine if calcium carbonate forms a precipitate when these solutions are mixed. Mixing the sodium carbonate solution with the calcium chloride solution yields a solution containing all 4 ions: calcium, chloride, sodium, and carbonate. Combine the ions to see which compounds are possible. Remember from your previous chemistry knowledge that only oppositely charged ions can combine. Since you determined in the previous scene that sodium carbonate and calcium chloride are soluble, the possible new compounds are sodium chloride and calcium carbonate. Refer to the solubility rules to determine if these compounds are insoluble. Using Rules 1 and 4, you know that sodium chloride is soluble and therefore does not form a precipitate. According to Rule 6, calcium carbonate is insoluble in water. Therefore, calcium carbonate will precipitate when the calcium chloride and sodium carbonate solutions are combined in sufficient concentrations. You will learn how to determine what concentrations are required to form a precipitate shortly. The type of reaction in the previous scene, in which a precipitate forms when two solutions containing different ionic compounds are mixed, is called a precipitation reaction. Precipitation reactions can be written as complete ionic equations and net ionic equations. A complete ionic equation shows the ions present before and after the reaction occurs, as well as any precipitate formed. In the last scene, you identified the ions and the precipitate. This information allows you to write the complete ionic equation. Looking at a complete ionic equation, you can see that some ions appear on both the product and reactant side of the equation. The ions located on both sides of the equation do not directly participate in the reaction and are referred to as spectator ions. By dropping the spectator ions from the complete ionic equation, you are left with the net ionic equation. In net ionic equations, only the ions directly involved in the reaction are written. Since the chloride and sodium ions are spectator ions, they are dropped from the complete ionic equation, which results in this net ionic equation. Now that you know how to determine whether a compound is soluble in water and how to write a net ionic equation, you will learn how to determine the ion concentrations necessary to produce a precipitate. Earlier you learned that Ksp is the product of the ion concentrations at equilibrium. Remember that a solution is saturated with ions at equilibrium. To determine if a precipitate will form, compare the Ksp value for the expected precipitate to a value called the ion product. The ion product is designated as Q and is determined using the ion concentrations in the reaction. The ion product equation is the same equation as the one used to determine Ksp. However, the Q value is calculated by multiplying the ion concentrations of a solution at any point, not just when it has achieved equilibrium. If Q is less than Ksp, a precipitate does not form. On the other hand, if Q is greater than Ksp, then a precipitate forms. A Q value greater than Ksp indicates that more ions are present in the solution than the solution can hold. Therefore, some ions precipitate out of solution to maintain equilibrium. For example, you are told that the ion concentrations of calcium ions and carbonate ions are 3.7 times 10 to negative 3 molar. Inserting these numbers into the ion product equation gives a Q value of 1.4 times 10 to negative 5. Using a Ksp chart, obtain the value for calcium carbonate, 4.5 times 10 to negative 9. You can clearly see that the Q value of 1.4 times 10 to negative 5 is greater than the Ksp value, 4.5 times 10 to negative 9. The solution is teeming with ions. Therefore, a precipitate forms until the ion product equals Ksp and equilibrium is reestablished. If, on the other hand, Q is calculated as 8.7 times 10 to negative 16, which is less than the Ksp value, 4.5 times 10 to negative 9, then the solution is unsaturated and the ions remain in solution. When Q equals Ksp, the solution is at equilibrium, and if more solute is added to the solution, the excess solute will not dissolve. Suppose you are asked, will calcium carbonate precipitate when half a liter of 0.1 molar aqueous solution of calcium nitrate mixes with half a liter of a 0.4 molar sodium carbonate solution at 25 degrees Celsius? At first, this may look like an intimidating question, and you might think, how do I even begin to answer this question? Remember, in order to determine whether a precipitate forms, you need to compare the Ksp value of the ionic compound to the Q value for the ion concentrations of the mixed solutions. As with all the other problems shown thus far, begin this problem by writing the balanced equation for the reaction, which shows that calcium carbonate is in equilibrium with calcium ions and carbonate ions. The next steps in the process of determining whether calcium carbonate forms a precipitate is to determine the ion ratio from the balanced equation and to determine the ion concentrations. The latter step gets a little tricky because you cannot simply plug in the given concentrations. You are mixing two solutions, each with a volume of half a liter. Therefore, the volume is doubled, because half a liter plus half a liter equals 1 liter. Since concentration is amount per volume, doubling the volume reduces the ion concentrations by 1/2. This is the reverse situation of what happened in the penguin example shown earlier. If 10 penguins are confined to a 10 square meter area, the concentration is 1 penguin per square meter. If the iceberg is doubled in area, then the 10 penguins occupy 20 square meters, or 1 penguin every 2 square meters. Now that a penguin is found every 2 square meters, the concentration of penguins is 1/2 the original concentration. Returning to the sample problem, you can determine the new ion concentrations of calcium nitrate and sodium carbonate, in addition to determining whether the concentrations are great enough to form a precipitate. You are given that the initial concentrations of the solutions are 0.1 molar for calcium nitrate and 0.4 molar for sodium carbonate. Reducing the initial concentrations by 1/2 determines the new molarity of each solution and results in values of 0.05 molar for calcium ions and 0.2 molar for carbonate ions. The next step in solving the problem is to write the ion product equation. Calcium carbonate is a solid, and therefore is given the constant value of 1, which is omitted from the equation. Now that the ion product equation is written, plug in the ion concentrations just calculated and solve for Q, which is 1 times 10 to negative 2. The KSP value of calcium carbonate at 25 degrees Celsius is 4.5 times 10 to negative 9. Comparing the Q value to the KSP value indicates that the Q value is much larger than the KSP value. Consequently, calcium carbonate precipitates. To this point, this program has discussed combining substances to form solutions or precipitates. However, science and industry are often interested in separating one or more substances from mixtures. Mixtures are either homogeneous or heterogeneous. As you learned earlier in the program, solutions are homogeneous mixtures because they contain substances that are uniformly mixed and in the same physical state. In contrast, substances in heterogeneous mixtures are not uniformly mixed, and they can occur in different physical states. A precipitate suspended in liquid, or a tossed green salad, are just 2 examples of heterogeneous mixtures. This program discusses 4 techniques used to separate substances from mixtures: filtration, crystallization, distillation, and chromatography. Suppose you have a mixture that contains a suspended solid, such as sand in water. To separate the solid from the liquid, pour the mixture so that it slowly spirals down the stirring rod onto the filter paper below. The filter paper contains small pores that allow the water molecules to pass, but prevent the sand particles from passing. As a result, the sand is separated from the water. Water is commonly filtered at home, while camping, or in pools. Certain pool filters use the simple process of filtration to clean debris from pool water. As water moves across the filter, Particles that are too large to pass remain on the filter. The filtered water is then circulated back into the pool. Occasionally, the filter must be cleaned to remove the built-up debris. In contrast to filtration, crystallization uses evaporation to separate dissolved or suspended solids from a mixture. During crystallization, the liquid evaporates, leaving one or more solids behind. This simple process is used in industry to make many types of salts. Seawater is either mechanically pumped into evaporation ponds or is carried into confined ponds by tides. Once in the ponds, the energy from the sun heats the seawater, causing it to evaporate. The evaporating seawater is moved through different concentrating ponds until the salts crystallize, which can be several years after the seawater enters the initial evaporation pond. The salts are then harvested from the ponds and further processed to remove impurities. Salts obtained through crystallization methods include those used in fertilizers, medicines, and table salts. Evaporation is also used in the process called distillation, in which liquids within a mixture are separated from one another based on the differences between the liquid's boiling points. During distillation, one liquid is converted to a gas at a temperature and the other remains a liquid. In addition, the gas is not allowed to escape in the distillation process as it is in crystallization. The vapor is sent through a device called a condenser, where it cools and returns to the liquid state, before being channeled to a container. The apparatus you see on screen is commonly used in the lab to distill liquids from a solution. Cold water flows around the outer tube of the condenser, which causes the vapor within the inner tube to cool, returning to its liquid phase. At this point, the pure liquid is condensed and then collected in a receiving flask. The final process of separating substances from a mixture covered in this program is chromatography. In chromatography, two phases of matter are used to separate substances from a mixture. One phase, called the mobile phase, carries the substances in question along the second phase, called the stationary phase. The separation of substances by chromatography is similar to the separation of people along a conveyor at the airport. The walkway around the conveyor represents the stationary phase, and the conveyor represents the mobile phase because it carries and separates people from one another as they move. As four people headed to the same gate step onto the conveyor, they begin to move towards the gate. Some people get off the conveyor at various stops. They represent the molecules that have a lesser attraction for the mobile phase, or conveyor, than the people who remain on the conveyor. The people who remain on the conveyor have a greater attraction to the mobile phase and arrive at the gate faster than the people who stop. Just as the people with a greater attraction to the mobile phase move along the conveyor more quickly than those who leave the conveyor temporarily, the substances with the greater attraction to the mobile phase move along the column more quickly. Gas chromatography can be used to test for pollutants emitted from the exhaust of cars. The exhaust is injected into a column, moving along with the mobile phase. A non-evaporative liquid within the column is the stationary phase. Separation of the gases depends in part on the gas's solubility in the liquid. The more soluble a gas is in the liquid, the faster it dissolves into the stationary phase, and the more slowly it moves through the column. In contrast, the less soluble a gas is, the more quickly it moves through the column. Located at the end of the column is a detector, which identifies and quantifies each gas as it exits the column. The readout can be compared to emission standards to determine whether or not the car tested exceeds the allowable levels of pollutants. This concludes the program on solubility and precipitation. During this program, you learned that temperature, pressure, and polarity affect the solubility of gases, liquids, and solids in solutions. Special attention was paid to the factors that affect the solubility of ionic compounds because they can form precipitates when mixing solutions. You have learned how to solve various problems, including how to calculate the KSP of an equilibrium reaction given the concentration of ions, how to determine the concentration of ions when given KSP, even in the presence of a common ion, and how to determine if a precipitate will form. Concepts of solubility and precipitation are not restricted to the lab. As you continue to learn these concepts, you will further your understanding of chemistry in the classroom, as well as chemistry in the world around you.